two in light, a strong base, and a weak cleavage. Yeah, same thing. So Br2 and light.
Wait, which one is this?
D.
D, yeah. So when do you know when to use a weak cleavage or strong cleavage? Strong cleavage creates CO2, right? That's about it? That's the only difference?
Yes,
strong oxidative cleavage?
Strong cleavage will give you an alcohol.
I'll give you an alcohol?
Cleavage won't give you an alcohol.
Wait, say that again?
Okay, so strong cleavage will give you an alcohol.
Okay.
Weak cleavage gives you an aldehyde.
Oh, okay, okay.
Sorry, acid, carboxylic acid. This is strong cleavage. Weak cleavage just keeps it as an aldehyde.
Okay, okay.
So that's, so if the end is an OH, like an O and an OH, you're like, how the fuck do I get that? You're going to want strong cleavage. Because it's going to be an aldehyde that turns into an acid or a carboxylic acid.
Okay.
So it's just, yeah, those endings. Then, so yeah, he got the same thing we got, and then a weak cleavage. So whatever you want to use for weak cleavage. Probably not a push-up bra if you want weak cleavage. I'm just gonna help myself. All right. Anyways, so the next one he didn't even try to do. So I did HBr and raw, and then I did Na plus minus 1, 2, 3. What was this shit attached to? 1, 2,
CHL.
1, 2, 3, 4. No, 2. No, I just did 2. Yeah. And then 3 hydroboration, and 4 was the oxidation part. Because I don't feel like writing it all out. Is that what you guys got?
I don't know. I don't know where my work is for this problem, so.
Well, we can go in steps, right? So the first one, this is your starting material, right? Is it? The first one gives you this. The second thing gives you 1, 2, 3. 1, 2, 3, 4, 5, 6. This gives you this, and this gives you this, which is what you want, right?
Mm-hmm.
So.
Wait, why did you put hydroboration oxidation as 2-step?
Oh, because it's a 2-stepper. So your step 3 would be the hydroboration part. Your step 4 is the oxidation part. Right.
Hydroboration is usually 1 step. Oh, wait. Oh, it's the 2 parts. The first part is the BR, the 2, and okay. Okay.
So that's that. That's the oxidation part. And then, yeah. So yeah, I just wrote it like that because I didn't want to write down the reagents because I'm lazy. But yeah, so you go from here to here to here, and that's how you get from here to here. Yes, we concur. So yeah, I had some questions about like the beginning. The monochlorination question. Is that in a slide or something that I missed? Does anybody know? Because I wasn't sure. Or was that in the book? I feel like I saw it somewhere, but then I didn't recognize the answers.
I didn't recognize this one either. I skipped it because I was like, oh, we're just gonna go over the reactions.
I don't even know what this is, so.
It's from the book. So I know Ling, we talked.
Chapter 10?
Huh?
Is it chapter 10? Like, you know, chapter?
Yeah, I think so, yeah. And what we learned is that chlorine is less selective than bromine, and it will go in more places than just the allylic position.
So basically, chlorine is a slut because it'll stick it anywhere.
Hey.
That's it?
Girls like to have fun too, Ling.
Chlorine is like, I'm gonna go anywhere I want, and bromine's like, no, I'm waiting for the special person. Okay, so I see. I think it's 453, page 4. No, that's, hold on. Selectivity. Okay, so it starts off page 450. Selectivity of halogenation. So, but I think it got me where it said monochloration products. And I feel like when they said monochloration, instead of just putting like Cl2, I got tripped up. I was like, wait, hold on, what does that mean?
Because we're not at CL2.
Yeah, so that just basically, you're just putting Cl everywhere then, basically, or what?
Yeah.
That's kind of what he did.
Yeah, the reason, so for instance, the two methyl groups on the far left, they only drew the chlorine attached to one of them because it would be the same product if you drew it on either. Does that make sense?
Oh, yeah, okay.
Or like the two methyls pointing downward, if you put the chlorine on one of them, it's the same thing as adding it to the other. So that's why they only drew one.
Okay.
And then they got the one wrong on the bottom right because you can't put a chlorine on a vinylic position. And then same with, yeah, both of the bottom answers are wrong because of that.
Yeah, I mean, this doesn't give you like a lot because the structure is very minimal, but like right there kind of tells you that the chlorine can go on both, like almost a half, whereas the bromine will only go on the most substituted.
Wait, so the chlorine is, why does it say 65% on the mono substituted plus?
What is that? Primary, oh, because of the reaction coordinate.
Wait.
I think I do remember this.
What I thought a tertiary radical was more stable. Yeah.
Yeah, this is just talking about chlorine. I think it was trying to say both cases carbon, but during chlorination, the amount of radical character is small. During bromination, the radical character is much larger. As a result, the transitions are more to the nature of the substrate during bromination. In the energetic chlorination, there's only a small difference in energy between transitions. In contrast, oh, I think it's because it's showing how if you, this is chlorine, right? So the energy difference between primary, secondary, and third and tertiary is very small. So like it doesn't, for it to be at a primary, secondary, tertiary, the energy difference is not a lot. So that's why it can go at either all three, like almost equal.
But why is the primary like double the amount?
I think like they were just, because I think down here in the explanation it says that it can even be up to closer to 50%. Like in this example, it's like if you look at it, it's kind of almost half and half. And even in the explanation on the following pages, it says how like the chlorination can almost be 50% because the energy levels, the energy of activations are so similar. Like they're not that much different. Whereas bromine is more selective because if you look at the energy of activation, tertiary is much smaller. So it's going to be like, it's going to get there faster than primary. Like primary and secondary, the energy activation is larger. So I really do think it could be almost equal amounts. Like the percentages will be relatively close, like maybe 40, 30,
yeah.
40% here, 30% here, 28%.
What page is that?
This is page 451 and 452, but the section starts at 450.
I think I watched a video on this. I'll find it and I'll send it because I was watching this and then I was like, oh, maybe we don't need to know this, but I guess we do.
Yeah, so I think problem D, I think the answer would have been just anywhere chlorine can go, which is a primary, secondary, tertiary.
Yeah.
So like the answer for this one, like all the places it can go here. These are the same, so that doesn't matter. It can go here. It can't go here because vinylic, right? It can't go here because it's already like it would violate the octet. And then it can go here, right? Because it'd be 3.
Yeah.
Yeah. So those are the only places it can go.
Yeah, and then the one where the chlorine was on the allylic position was the major product.
Yeah, that would be the major product because it's the most stable. So Cl can go here, or well, that's the same. Hold on. Cl can go on the end and then can go here, right? Does that make sense what I'm saying? Would that be both?
Wait, sorry, what'd you say?
So like the black is the original, right? So Cl can go here, which is the allylic. It can go here.
Mhm.
It can go here.
Mm-hmm.
And can it go here? That's like a different product, right?
Oh, yeah, you're right. It can go to the tertiary.
Four places.
Yeah.
So yeah, as long as it doesn't violate the octet rule and it doesn't create a unstable carbocation or like whatever, it can go there.
It's cool.
All right. So
Yep.
yeah, that's cool because that was my only question. I was like, I don't fucking know what they're talking about. All right, guys. Well, hopefully tomorrow we're gonna come all with questions.